First, I want to thank all the organizers for their efforts in organizing this workshop and as well as the long-term program. And I really appreciate I have a chance to give my talk here. So I'm doing like very pure mathematical analysis and PDE, and I would apologize if there are too many mathematical details in this talk. And on the other hand, maybe this can give you some different flavor at the end of today. So the model I want to study is actually, so I study fluid dynamics, which is my background, but this model, it's like coupled Nernst-Planck with some fluid model. And Nernst-Planck we know is about electrodiffusion, so hopefully it fits the topic of this workshop. Okay, so this is the outline of my talk. So first I will review some background about Nernst-Planck-Navier-Stokes equation, system which is already widely studied. It's coupled Nernst-Planck with the most famous fluid model, Navier-Stokes. Okay. And then after that, I will introduce the Nernst-Planck, and then I want to couple it with some other fluid model, which is the Boussinesq system. And here we will consider the evolution of the temperature as well as the effect of the buoyancy force. And then there are two results I want to report. The first one is global existence of weak solution in the three-dimensional case. And the second result is the long-time dynamics of these weak solutions and their convergence to the steady state. All right, so first, I don't have too many pictures. This is the only page has a picture which we'll show later, but it's an introduction of the electrodiffusion. So it's a phenomenon describing the diffusion of ions under the influence of an electric field induced by ion charge themselves. So it has many applications, and I'm pretty sure, like many experts in the audience, you are more familiar with the applications. So anyway, it has many applications in neuroscience, semiconductor theory, water purification, and desalination, and ion separation, etc. So one of the applications is about the battery. So suppressing the dendrite growth will significantly improve the performance of the battery. So electrodiffusion near the dendrite nucleation site can change the local mass transport and ultimately affect the dendrite growth. Okay, so now after this, I will talk about the mass. So this page is the introduction of Nernst-Planck. So we talk about electrodiffusion of ions, and it's described mathematically by Nernst-Planck's equation. I will use NP for short abbreviation. So here we have evolution equation for Ci. And here Ci, they are non-negative function. They represent the ionic species concentrations. So they need to be non-negative. And the Ji, they are flux of the I species. And there are three components. The first one, UCI, so U is the velocity. So this represents the advection. So the concentration is advected by the fluid. And the second term is the diffusion. And the last term is the electromigration. Okay, so there are three components. Each of them have some meaning. And we also have this Poisson equation, which is the negative epsilon Laplacian per psi equals to the charge density, where the charge density is the Faraday constant times the summation of Zi/Ci. And here, these are all the quantities. I will go through one by one. So psi is the electric potential, rho is the charge density, U is the velocity field, and the T here is the absolute temperature. And Di, they are constant, they need to be positive, they are diffusivities. And Zi, they are also constant, they are valences. And Kb is the Boltzmann's constant, E is elementary charge, epsilon is the dielectric permittivity of the solvent, and Na is the Avogadro constant here, and F, again, is a Faraday constant, is equals to E times Na. Okay, so for the electromigration term, we can, instead of EZI over KBT, we can also write it as FZI over RT. It's just, these two forms are the same. Okay, and here R is the molar gas constant. So what I'm interested in is actually later I will explain. So here in the mathematical literature, as far as I know, most of the work, they take the temperature to be a constant. Okay, so of course this I know it definitely makes some sense. It's like approximation, but what happens if we take the temperature to be a variable? It will be very interesting mathematically because it appears in the denominator. So it will make this term, which already nonlinear, we will make it much more nonlinear. So 1 over t is very nonlinear. Okay. So this is about the Nernst-Planck. And so far, if we only have Nernst-Planck, usually the U is given, the velocity field is given. But more general, we can also think about the U itself is not a given quantity, is also unknown. And in this case, we need to couple it with some fluid model, depends on what's the phenomenon we are interested in. Okay? So if we are interested in the fluid which is incompressible, viscous fluid, then we will couple it with this incompressible homogeneous Navier-Stokes. Homogeneous means that we assume the fluid density is a constant. Okay. So here, this is the Navier-Stokes. The left-hand side, we have delta U plus this advection term, and the viscosity term, and the pressure gradient. And the right-hand side is the electric force. Okay, so if we don't have the ions, then the right-hand side is 0 or some other external force. Here we have ions, so it will be this electric force. And it's divergence free because it's incompressible. So the coupled system, we couple this with the Nernst-Planck. The coupled system will be called Nernst-Planck-Navier-Stokes. So for this system, it's typically studied, we are interested in either the bounded domain case, and the dimension D is either 2 or 3, and all torus, okay? And if the domain is a bounded domain, then we need some boundary condition. So for the velocity, we can take it to be a homogeneous Dirichlet, namely no slip boundary condition. And for the potential, we can apply some voltage on the boundary. So it's also Dirichlet, but not necessarily homogeneous. And for ionic concentration, there are many different types of boundary conditions. And here I list 3 of them. The first one is called blocking boundary condition. It means that the flux of ions, the normal direction of the flux is 0 on the boundary. And physically, it means that the boundaries function as impermeable barriers, prevent the ions from crossing them. Okay, so it blocks the ions. And the second type is the Dirichlet, namely we assume the ionic concentration is some given function on the boundary. And in this case, ions are allowed to pass through the boundary. Okay, so it's called ion selective membrane that uphold a fixed ionic concentration. And the last one is the mix of the previous 2. Like you can think about the boundary can block certain type of ions, but allow other type of ions pass through. And here I try to list some like mathematical problems we want to study for this model. So here we are interested in under different boundary conditions and different ionic settings. What I mean by ionic settings is that we can have different number of species in our system. The most simplest case is like if we have only 2 species, okay? Then, and we can also have arbitrary n species. And also we are interested in different relation of the valences. The simple case is that if we can assume the absolute value of all Zi are the same, that's a special case. It will simplify the analysis. And also the diffusivities, we can, actually in this course, I have to assume they are all equal. But more general, the diffusivity can be different. So here is the list of some mathematical problems. So first one is about the existence of solution. And so in Matthew's talk, he also mentioned about the weak and strong solution. So weak solution basically means it's in the integral form, like distributional sense. And a strong solution means that it makes sense almost everywhere in space and time. And after the existence, we are interested in like uniqueness and continuous dependence on the initial data. So the 1 and 2 together will be well-postedness. You may hear about this terminology several times, but basically well-postedness means existence, uniqueness, and continuous dependence. And also the long time dynamics, when time goes to infinity, what happens to the solution of the system? And the stability of steady state, especially the Boltzmann steady state. If we perturb around this steady state, will the perturbation remain small or not? And also some interesting phenomena like interior electroneutrality. Of course, this has been observed from the experiments, but we are also interested in to justify it mathematically. Okay? And there are many other problems. So here is a very incomplete literature about Nernst-Planck-Navier-Stokes. So we already have the existence of global weak solution in 3D. Okay, this is done by Jerome and Sacco, and the same year by Raham and Skalmark, and later by Fisher and Saul. And Konstantin and Ignatova, they have several works later. So the first one is that they consider the smooth bounded domain, and they prove the global existence and uniqueness in 2D, as well as the convergence to the steady state. And with Lee, they also proved the nonlinear stability of the Boltzmann state in 3D and interior electroneutrality. And with periodic boundary condition, we have the long time dynamics and also analyticity of a solution by Abdo and Ignatova. And people also study Nernst-Planck coupled with some other different fluid model, including the Euler and the Darcy. Darcy means Darcy law. It's like we consider electrodiffusion in porous media. So we replace Navier-Stokes by the Darcy law. All right. So for Nernst-Planck-Navier-Stokes, there are some mathematical challenges. I will briefly talk about that here, and also some strategy. How do we overcome those? So the main challenges comes from the electromigration term. Okay, here. So for Nernst-Planck-Navier-Stokes, we take temperature to be a constant. But even if temperature is a constant, this term is already very bad, very nonlinear. And think about if we want to do the L2 estimates of the ionic concentration Ci, we need to take inner product of this term with Ci, and then we integrate, right? So we can do integrate by parts. We can move this divergence to Ci, make it grad Ci. But this term, if we estimate it, it will result in CiL2 to some power k, where k is strictly greater than 2 depending on the dimension. And this estimate only allows a local solution in time, which is, of course, not something we want to pursue. At the end, we want some like global solution, especially in 2D. So what we can do, the first special case is that if we have only 2 ionic species, and we assume they have the same diffusivity and opposite valences. And we will introduce a new variable called sigma, which is F times their valences, because they are opposite, so I just take it Z, times C1 plus C2. So observe that this quantity is non-negative. And recall that our charge density is rho is given here. Okay, so now we can write down the evolution for sigma and rho. And now if we want to study the L2 evolution of both sigma and rho, the migration term, we add them together and we will do the integration by parts. It will turn out to be something good, which is a dissipation. So it has a good sign because here sigma is non-negative. So this way, it turns the bad migration term into something good, at least not our enemy. So it can allow us to do the L2 estimate and proceed later. Okay? But of course, this is when we have this special situation for ionic concentration. And more general, if we have, say, n ionic species, different valences, different diffusivity, we need to study the relative entropy, the KL divergence. So here is the relative entropy between Ci and some Ci star, where Ci star is the Boltzmann steady state. So it's actually given explicitly here. Okay, it's the solution of this equation. Right. So now let's continue. So this is about the So the limitation of the current existing electrodiffusion model, mainly something I already mentioned is that the firstly is the temperature. Okay, we assume before we assume the temperature to be a constant, and it will simplify the migration term. And secondly, the salinity term resulting from the variation of the concentration and the temperature has been disregarded. So I actually asked some experts here, and you can also say, okay, the fluctuation of the temperature and maybe the effect of buoyancy are almost negligible, so which means their magnitude can be very small. But mathematically, what's interesting is not just the magnitude, it's about the regularity. So even though the temperature is not, as long as the temperature is not a constant, even though the fluctuation is small, it will create the gradient of T. Okay? And it will affect the regularity of the equation, and therefore, when you do the analysis, it will give us some challenges. So instead of Navier-Stokes, now I want to change my fluid model. I will consider the Boussinesq approximation. So it looks long, but I will explain one by one. And actually, you can see there is a word approximation. It actually means that for the momentum equation, we will assume that the fluid density is homogeneous except in the buoyancy term. Okay? So it's a fair approximation has been widely used. So now for our momentum equation, the left-hand side is the same as Navier-Stokes, but the right-hand side we have additional term, which is the buoyancy term. So G is our gravity constant, K is the vertical vector, and beta is our fluid density. And our fluid is still incompressible. And the density can be explicit written as expansion like 1 homogeneous part minus the effect coming from the fluctuation of the temperature and the fluctuation of the salinity. Where TR and SR, they are just some reference value for the temperature and the salinity. Okay? And for the temperature, we consider it is transported by our fluid and diffused. And finally, here, S salinity is the summation of Ci times the molar mass of ice ionic species. Okay? So what I'm trying to do is that I want to couple the Nernst-Planck with this system, with this Boussinesq system. So this is the result of the coupling, and I will call it NPB system. So the first equation is my Nernst-Planck, and second equation is our Poisson equation. And the 3, 4, 5, they are the Boussinesq approximation. Okay? So the coupled system is my NPB system. So the unknowns are Ci and the potential, and also velocity, the density, the pressure, and the temperature. Okay. So the relation, yes.
Can I ask a question?
Yes.
So this is all really interesting. I'm asking to some extent coming from a physics or materials background. When we think about thermal gradients, so the temperature not being constant, that's what you're trying to consider,
yes,
right?
Yes.
There's two other things we often find important.
Okay.
And I'm not sure if you're neglecting them, approximating them to be relevant here or not. Just curious. The first one is you have thermomigration, so that you also get diffusion due to the temperature gradient. There's an on-Saga term for that.
So it will appear also in
There's a gradient T times some transport coefficient gives you a flux of the ions.
Okay.
It's an extra term.
Okay.
If you ignore that now, that's fine. I'm not complaining.
Okay.
I'm just saying it might be fun for another project.
Yeah, sure, yeah.
And then the next thing is the biggest temperature dependence that at least I teach in the class when I talk about diffusion and there's temperature gradients is that 1 over T term, we just say that's completely negligible compared to the temperature dependence of the diffusion coefficient, which follows an Arrhenius behavior. Right? In solids, in liquids, it's only a T to the 3/2. So in liquids, that might actually be really good what you're doing here, but there's still that D depends in liquids as is proportional to T to the 3/2 in liquids.
You mean the
it's not a constant in a liquid.
Diffusivity. Yeah. Okay.
Yeah, just curious.
Okay.
You're ignoring that right now, right?
Yes.
That's fine.
Okay, yeah, thanks for the question and the suggestion.
I'm just giving you more projects.
Yeah, okay. Yeah, actually, one of the big reasons I attend the workshop is I want to learn more about like maybe some good way to also do the derivation of some new modeling. And Okay, thank you. Thank you. Okay, so quick relation between NPB and NPNS is that if we take the temperature back to the constant and neglect the salinity effect, then we will go back to the NPNS system. So the NPNS system is a special case of the NPB system. And we will, as this is just a new model, so I don't want to study the effect of the boundary. Instead, I will just consider the torus, because torus, everything will be much easier, so that our focus can be just on the equation itself. And in this case, the reference temperature and the salinity, they are just the spatial average. And we can also compute that they are invariant in time. So this TR and SR, they are just some constant totally determined by the initial condition. Okay? So they are the spatial average. And the important property of the CI is that we know, of course, the concentration cannot be negative. So we have to assume that initial data, they are non-negative. And we can justify that it remains non-negative if the solution is regular enough, mathematically. Okay. Okay, so our goal, so the first result I want to report is about the global existence of weak solution. And what we need to do is we need some global in time estimates. So I will do a lot of energy estimates here. So the first challenge is that the T appears in the denominator. So of course we don't want the denominator to be 0. But we know the temperature is absolute temperature. So by the third law of thermodynamics, we know it's strictly bounded below by some positive constant. And by maximum principle, because the temperature itself satisfies the evolution, is transport and diffused. So it satisfies the maximum principle. So for any later time and space point, the temperature is also bounded below by this T star. And so all challenges in Navier-Stokes part remain also in the Boussinesq system, but things can be worse. So one simple example is that if we still consider the case I mentioned earlier, two species, the same valences, opposite valences, the same diffusivity. Before we only have this black part, but if the temperature is not a constant, and we also do the integrated part, so it will produce this new red tone. And red usually in my talk will be something bad, okay? So here this red tone is no longer under control. And there are also, for the Nernst-Planck-Navier-Stokes, in the general case, we can use the relative entropy and together with some other energy together. But those dissipation structure will break down. And again, the main reason is that integration by parts will introduce some bad terms involving the temperature as well as its derivative. And also, finally, the salinity term is like some forcing term. In the momentum equation, will require some control of CI. Okay, so which I will explain later. Okay, so here you don't need to worry about it looks giant, but you just need to know the effect of each term. So firstly, we will do the estimates of the relative entropy, which is the relative entropy between CI and the CI star. So in our case, CI star is actually the spatial average, right? We mentioned earlier that we are interested in the torus. In the torus case, the reference is just the average. So here, the estimate, the time evolution of the relative entropy will give us some dissipation. Let's call it dA. And the right-hand side is just some giant, ugly, nonlinear term. We call it N. Okay. So, compared to Nernst-Planck-Navier-Stokes, here for Boussinesq, because the temperature is a variant, we have to consider the diffusivity are all identity. Okay, that's an important assumption. So in this case, we can have a good evolution equation for the charge density. The way we get this equation rho is that we go from the equation of Ci, we multiply it by Zi, and we take all the summation, because that's how we get rho. Okay? And in particular, this term, which is actually the dissipation, we have this good structure because all the di's are the same. Otherwise, this term will not be in this form. It will be ugly. So we will study the L2 norm of the gradient side, which is also the H-1 norm of the charge density. It will give us two additional dissipation. The first one I use orange means it's not that important. And the second one we use blue is some good term, a dB, okay? And on the other hand, we again get some bad term on the right-hand side. So blue is good, red is bad, okay? So these two terms, dA and dB, they will together, they can control the N here. They can control the N. That's the key story. And here, a remark about this assumption again. So if we don't have this assumption, then in general, we will have this negative d Laplacian rho. It will be in this form. So it's not a dissipation term anymore, and it will cause some trouble. Actually give us some bad term in the analysis. Okay, and also another remark is that if di are different, the corresponding dB term, so the dB term will also not be in this form. It will be something else. And in that case, dB is not good enough to control the N on the right-hand side. Okay. So here I just try to explain why this assumption is important in the analysis. And okay, so finally, we also have to control this term. Okay, and actually, this is something easy we can do. We just also consider the estimate of the kinetic energy, L2 norm of U, and it will remember the momentum equation on the right-hand side. We have the electric force, so it will cancel with this red term from here. Okay, but on the other hand, when we want to estimate the kinetic energy, we have to control a term, something like U times Ci. This term comes from the salinity. Okay, and why I want to emphasize the difficulty of this term, because we do not have the L2 control of Ci. So we have to do some. Actually, it's not hard, but it's interesting to mention here. So firstly, dA and dB in previous page, the two dissipation, the joint dissipation term, they will give us a dissipation, which is the gradient of the square root of Ci. And now, for this UCi, I can decompose it into U square root of Ci, square root of Ci. And then I use Holden inequality. I put L3 on each of them, and I do the interpolation inequality. So in particular, for example, if we do the L3 estimate of square root of Ci, it can be controlled by L2 norm 1/2 times H1 norm 1/2. So the H1 norm can be controlled by the dissipation. And what's the L2 norm of square root of Ci? It's just the L1 norm of Ci. But Ci is non-negative, so it's just the spatial average. And we know this spatial average is a constant, which depends on initial data. So basically, this term is just a constant. We don't need to worry about that. And all this can close the energy estimate and give us the global existence of weak solution. So, okay. So here, I probably will skip some details. Those are actually, like I want to talk about the proof of the global existence of weak solutions. The main ingredient I already mentioned is the energy estimates. And for the rest, it's just some classical framework. So we need to regularize the system, either use Gherkin or some modifier. But here we don't use Gherkin because Gherkin will destroy some good structure of our equation, especially, for example, the maximum principle of the temperature. And also it will cause the ionic concentration become negative. So the Gherkin method is not good. Instead, we will use the modifier operator. So here, we just need to know that J eta is a modified regularized operator. For each eta between 0 and 1, we want to regularize the system, and we don't need to regularize all the terms. We just need to regularize the advection term as well as the potential term. And we also regularize the initial data. Okay? And So this is a remark about if our initial condition, which is non-negative for concentration and strictly positive for temperature and mean free for the velocity, it will imply that all these modified quantities also satisfy these properties. So another important reason we use modifier is that it can keep our good properties of these quantities, like the concentration and the temperature. Okay, so here so I can speak. So this part is just some initial data we need to impose for the original NPB system. For the so let's see the proposition 1. It's about the global well-posedness of our regularized system, the eta system in previous page. So for this eta system, we regularize the system and also the initial data. So we definitely can expect global well-posedness. And actually the solution, they are C-infinity smooth. Okay. So, and this is just proposition, it's not hard to prove. This is maybe like some exercise a graduate student can do. We can do the linearization and then prove the uniform bound in terms of the iteration steps. And we can prove that the global well-posedness. So far we can, for each eta, we can have some good solutions, Ci eta, U eta, and T eta. And the next step is that we want to pass to the limit that eta goes to 0, and when these solutions converges to something, and those something will be the solution of our original Nernst-Planck-Boussinesq system. Okay, so this proposition 2 and 3, they are uniform bounds we need to pass to a limit. Actually, proposition 2, we already talked about that. It's the uniform, it's the estimates we mentioned earlier here. Okay, it's this part. Okay, so in particular, we have the regularity for square root of Ci eta, the temperature T eta, and the velocity U eta. So they have some uniform bounds. And this uniform bounds, by the very classical Banach-Alaoglu theorem, we can have some weak star or weak convergence. But because, and this is not enough because our system is nonlinear, and in order to prove the convergence of nonlinear term, we need some strong convergence. For that, we need some compactness theorem, especially the Obindio's compactness theorem. And for that reason, we need also the uniform estimates of the time derivative of each unknowns. And you may see that this term is very funny. It's like square root of Ci plus 1. I will explain just in a second why we plus 1 here. Okay. So I will skip this page. It's the uniform in time as uniform in eta estimates, which we already explained. But here I just collect them. Okay. So proposition 2, you trust me, we have that. Okay. And then finally, just make a comment about the time derivative estimate. So if we just take the time derivative of square root of Ci eta, the square root of Ci will appear in the denominator, which might be 0. Okay, the concentration can be 0. So the plus 1 is just to avoid the denominator from vanishing. Okay, it's just some technical trick we need to do. Okay, so we also have the time derivative estimates, and combined with proposition 2 and 3, which is the estimate of the solution and the time derivative, we can get all the convergence we want, either weak or weak star or strong convergence. Okay, and again, these are based on Banach-Alaoglu theorem and Obindio's compactness theorem. And once we have this convergence, we can pass to the limit for this U eta k, Ci eta k, T eta k. And we pass to the limit and then prove that the limit is exactly the solution we want, the weak solution. And maybe one comment I want to mention, why here we only do weak solution? Because we are interested in the 3D case. And the 3D case, we have Nernst-Planck part, we have Boussinesq part, which also has the Navier-Stokes part. So if we want a global solution for 3D Navier-Stokes, we can only hope the weak solution. There is no way to get strong solution. That's the Millennium Prize problem. Okay, so this is the theorem we have. This is work with Abdul and Hu. So suppose some initial condition, you don't need to worry about that. And also the T naught here, instead of L2, we need it to be slightly better than L3. Then for any time, here, once you see any time, it means global solution. There exists a weak solution, Ci, U, and T, which with this regularity, such that Ci are non-negative, and the temperature is bounded below by T star, almost everywhere. Okay? And this property comes from that the regularized solution, they satisfy this property. And we have certain convergence, and therefore we can justify the limit also satisfy this property. And one more remark, like a slightly artificial regularity requirement for the temperature is because the electromigration term is too nonlinear. Okay? So L2 and even L3 will not be enough. We need slightly better than L3. Okay, so that's the existence of weak solution. And the second result is about long-time dynamics. We are interested in what happens when time goes to infinity for this weak solution. Because this is a dissipative system, so hopefully it can converge to a steady state. That's something we want to prove. And this is the result we have. So suppose that CIUT is a weak solution to system 2. So I use a because we do not have uniqueness. You may have many different type of weak solution. Okay? But here we are interested in the weak solution from system, from the way we prove from theorem 1. Then, firstly, the temperature will decay exponentially in time to the initial average in L2, and this convergence is unconditional. But for the velocity and the concentration, we need some size condition, and that's the reason I keep all the parameters. Actually, usually in analysis, we will assume like all the D, R, nu, alpha S, they are all 1. But here I keep all of them just to try to see what's the size constraint here. So the maximum of the initial average of the concentration needs to be not that large. And the right-hand side is exactly the size condition. If we have such a condition, then Ci and U will decay exponentially in time. So Ci will converge to its initial average. So return back to the homogeneous case. And then U will goes to 0. Means there is no fluid moving anymore in L1 and L2 respectively. And moreover, the relative entropy will decay exponentially in time to 0. Because again, we are talking about electrodiffusion, so everything will diffuse. And in particular, if the salinity effect of the buoyancy is negligible, namely alpha S is 0, then the right-hand side becomes infinity, so you don't need to put any assumption on the sides of the initial ionic concentration. Okay. So I have a little bit more time. So here, just give you a little bit proof. Recall that the energy estimate we have is like we have the d by dt of this part, the orange part is our energy, is the linear combination of L2 naught of grad psi, L2 naught of U, and our relative entropy. And the blue part, they are the dissipation. And the right-hand side, we have the something coming from the buoyancy force. The first term is not that bad because our temperature converges to TR unconditionally and is exponential decay. And the second term is the salinity term, and I mark it as red, which means bad. Okay. Okay. So first, let's look at this energy. We have 3 terms, and the dissipation there are also 3 terms. So firstly, I can use some inequalities to control the energy by the dissipation. The first one, we can use just elliptic estimates, okay? And the second one, the U-turn, we can use Poincare inequality because we have mean-free property for the velocity. And the last one is more interesting. We need to use logarithmic Sobolev inequality. So the L2 north gradient square root of Ci can control the relative entropy. Okay? So in a word, the blue turn can control the orange turn. The dissipation can control the energy. And it's the reason at the end we can get the decay of the solution. Okay, and here is some detail like why we need the size condition. So the red turn on the right-hand side will destroy the decay because by groundwater, it will actually give the growth of the solution instead of decay. So it comes from the salinity term in the momentum equation, so we can revisit the estimates. So instead of estimated by this guy, this red guy, we can estimate it purely by the dissipation. And if we want to control these two terms by the dissipation, we need some small size condition on this part, okay? So if we have this size condition, which is exactly mentioned in the theorem, then the orange term can be totally absorbed by the dissipation. And at the end, we can, by groundwater inequality, we can have that the energy, all energy, like this orange part, it will decay exponentially in time. And this is for the weak solution eta, and then we can argue that in some sense that when eta goes to 0, we have the convergence of our solution to a weak solution. And the weak solution, the energy of the weak solution also decays exponentially in time. And now in particular, we can see that U goes to 0. So the L2 norm of U goes to 0, which means U itself goes to 0. Secondly, the relative entropy goes to 0, okay, exponentially in time. And what about the concentration? So finally, to control the concentration, we use this Caesar-Kullback-Pinsker inequality. So L1 norm of the Ci minus its spatial average can be controlled by the relative entropy. And therefore, Ci will decay to its, not decay, like Ci will go to its homogeneous average. Okay, so that's the long-time dynamics. Some conclusion. Okay, so the main difference and challenge between this new system and other electrochemical diffusion model are the non-constant temperature and the salinity. And so we have the global existence of 3D weak solution when the ionic diffusivity are all identical. And we also have the exponential in time decay of the solution, but we need some size condition on the initial ionic concentration. And of course, there are many interesting future questions we want to answer. It's like here we study, firstly, like some assumptions, can we drop them, okay? Like the identity or identical ionic diffusivity, and also the size condition of the concentration. And also, this is a study on torus, and more interestingly, we need to study it on bounded domain and see what's the effect of the boundary condition. And in that case, the Boltzmann steady state will be much more interesting. And of course, study their stability. And something I didn't put here is that I also want to learn, as Richard said, also how to maybe derive more physical, meaningful electrodiffusion model under the non-isothermal setting, and also study the mathematical property of those models. Okay, so I will stop here. Thank you very much.